Hello everyone, welcome back. My name is Hako and this is the first video of the series of Generative AI Foundations. In this model, we're going to break down how large language models actually work, what embeddings are, how to talk to these models through APIs, and how to control their behavior. If it's the first time you've been here, please check out the description below. I will be uploading the link for our community so you can practice these exercises, hands-on exercises, and not just look at this video, because this video covers core concepts, what's happening under the hood. And yeah, we're gonna break down every single topic. So yeah, without any further ado, let's jump right in. So what is a large language model? Let's break that name down. Large means it has billions of parameters. We will explain what those are in a second. Language means it works with text. Model means it is a mathematical program that has learned patterns from data. Here's the key idea. An LLM is a program that was trained by reading billions of pages of text from the internet, books, Wikipedia, code, forums, everything. From all the reading, it learns patterns about how large language works. Those patterns are stored as numbers called parameters. You can think of parameters like the settings on a massive equalizer with billions of knobs. Each one tuned just right so the model can produce coherent text. Now, LLMs do not work with full words directly. They break text into pieces called tokens. A token might be a whole word like hello, or it may be a piece of word like un, and believe, and able to form unbelievable. This is important because the model thinks in tokens, and you get charged per token with using APIs. On the right side, you can see how a human brain learns language versus how an LLM does it. The process is very different, but the results is surprisingly similar. Here's the core idea that everything else built on. LLMs generate text by predicting the next token, one at a time. You give it like the cat sat on the, and it looks at all those tokens and calculate probability for every possible next token. Matt might get 15%, floor gets 12%, chair gets 8%, and so on and so forth. Then it picks one, usually one of the high probability ones, and adds it to the sequence. Then it does it again for the next token, and again and again. That is how you get full sentences and paragraphs. Now, the context window is another important concept. This is how much text the model can see at once when making predictions. Think of it like short-term memory. GPT-4 can see about 128,000 tokens at once. That is roughly a 300 page book. Old models could only see about 4,000 tokens. If your conversation gets longer than the context window, the model literally cannot see the earlier parts anymore. Look at the code block. Those probabilities are simplified versions of what the model actually computes. In reality, it's calculating probabilities across its entire vocabulary of tens of thousands of tokens. Let's quickly touch on transformers and attention, because you will hear these terms a lot. The transformer is the architecture, the blueprint that all modern LLMs are built on. It was introduced in a famous 2017 paper called Attention is All You Need. I will leave the description below of the paper. Before transformers, models read text one word at a time, left to right, which was slow and made it hard to understand long passages. The key innovation is something called the attention mechanism. Here's the intuition. When you read the sentences, the bank by the river was steep, your brain instantly knows bank means of a riverbank, not a financial bank, because you pay attention to the word river. That is exactly what the attention mechanism does. It lets each token look at every other token in the input and figure out which ones are more relevant to it. So when processing the word bank, the model assigns high attention weights to river and steep, which helps it understand the correct meaning. You don't need to understand the math behind this. You know that attention is the secret sauce that lets LLM understand context and relationship between words, even when those words are far apart in the text. Alright, now let's talk about embeddings. This is one of those concepts that sounds intimidating, but it's actually super intuitive once you get it. An embedding is just a list of numbers that represent the meaning of a piece of text. Think of it like GPS coordinates, but instead of representing a physical location on a map, they represent a location in a meaning space. Words with similar meanings end up with similar numbers, so they land close together in the space. Look at the table. These are hugely simplified examples. Real embeddings has hundreds of thousands of numbers, not just 3. But the idea is the same. King and queen have similar values because they are both royalty. Puppy and dog are close because they are both, well, dogs, right? But king and banana have the very different numbers because their meanings have nothing in common. The reason this matters is that computers cannot understand words directly. They need numbers. Embeddings are how we convert human language into numbers that capture actual meaning, not just random IDs. So, how do we actually measure if two embeddings are similar? This is where cosine similarity comes in. Picture two arrows pointing from the center of a circle. If both arrows point in almost in the same direction, the angle between them is small, and the cosine similarity is close to 1, meaning the words are very similar. If the arrows point in completely different directions, the angle is large, and the cosine similarity is close to 0, meaning the words are unrelated. You do not need to memorize this formula. The key takeaway is cosine similarity gives you a number between 0 and 1 that tells you how similar two pieces of text are. A score of 95% means very similar meaning. A score of 20% means not related at all. This is incredibly powerful because now we can do math on language. We can ask questions like, which of these 10,000 documents is more similar to this search query? That is essentially what semantic search does, and we will see that next. So where do embeddings actually get used in the real world? The big three are semantic search, recommendations, and clustering. Semantic search is probably the most common. Traditional keyword search looks for exact word matches. If you search for how to fix a flat tire, it looks for pages containing those exact words. Semantic search using embeddings understand the changes and punctuated wheel means the same thing, even though it shares 0 words with your query. Recommendations work the same way. If you like an article about Python data pipelines, embeddings can find articles about ETL automation because they are close in the meaning space, even if they use completely different words. Clustering is when you take thousands of documents, computer embeddings, and group them by similarity. Customer support tickets, survey responses, product reviews, you can automatically organize them into categories without writing any rules by hand. These are the workhorses of modern AI applications, and understanding embeddings is what makes them possible. Alright, let's move on to how you actually talk to these models through APIs. Okay, API stands for Application Program Interface. Think of it like a way your code sends a message to a server and get a response back. Here's why APIs exist. Running a model like GPT-4 requires specialized hardware GPUs that cost tens of thousands of dollars. Instead of buying the hardware, you send your text to OpenAI or Anthropic over the internet. Their servers run the model and they send back the result. You pay per token, typically a fraction of a cent per 1,000 tokens. The whole round trip usually takes 1 to 5 seconds. The way you talk to an LLM through an API is by sending a list of messages. Each message has a role and a content. These are 3 roles. System is the behind-the-scenes instruction that sets the personality and rules. The user never sees this. User is the human's message, the questions or request. Assistant is the model response. When building a chatbot, you send the entire conversation history each time so the model has context. This messages pattern is the same across almost every provider. OpenAI, Anthropic, Mistral, you name it. Here's a complete working example. We create the client, build our message, and call client.chat.completions.create. The response has choices containing the model's response, and usage telling you how many tokens were consumed. This matters because you pay per token. One more thing, never hardcode your API key. Set it as an environment variable. That's a security best practice from day one. Alright, so we have been talking about LLMs, how LLMs generate text. They predict the next word, or more accurately, the next token. But here's the next thing. When the model predicts the next token, it does not just pick one. It actually calculates a probability for every possible token in its vocabulary. We're talking tens of thousands of options. Temperature is a number that controls how the model picks from those options. Think of it like a creativity dial. A low temperature, like 10%, makes the model very conservative. It almost always picks the single most likely next word. A high temperature, like 1.5, flattens out those probabilities, making it more willing to pick less like words, which leads to more creative and sometimes surprisingly output. Check out the comparison here. Same prompt, totally different vibes depending on the temperature setting. Okay, so temperature controls the randomness, but there are other knobs you can turn to. Let me introduce two more, top P and top K. These are called sampling strategies. So here's the deal. After the model calculates probabilities for all possible next tokens, instead of considering every single one of those tens of thousands of options, you can tell the model to narrow down the candidates first, then pick randomly from the smaller pool. Top K is a simpler one. You just say, hey, only consider the K most likely tokens. If K equals 10, the model looks at the top 10 most probable words and ignores everything else. Top P, also called nucleus sampling, is a bit smarter. Instead of a fixed number, you set a probability threshold. If P equals 90%, the model finds the smallest set of tokens whose combined probabilities add up to 90%, and only picks from those. This means sometimes it might consider 5 tokens, sometimes 50, depending on how confident the model is. Check out the table for when to use what. So now the big question, what settings should you actually use, right? Here's my practical cheat sheet. For production systems where you need consistent, repeatable results, like a customer support bot or a data extraction pipeline, go with temperature 0 and a low top P. This gives you reproducibility, meaning the same input produces the same output every single time. For code generation, keep temperature low but not 0. A tiny bit of randomness can help the model explore slightly different but valid solutions. For creative tasks like writing, marketing copy, or brainstorming, crank it up. And here's the key insight. Usually you only need to adjust one of these at a time. Start with temperature and leave top P at 1. Only tweak top P if you need finer control. Most developers never even touch top K, And remember, the best settings depend on your specific use case. Experiment and see what works. Alright, here's a real problem. You will hit when building applications. LLMs return plain text, just a big string of words. But in real software, you need structured data. Things like JSON with label fields your code can read. If you ask an LLM to analyze a customer email, you don't want a paragraph. You want a clean JSON object which feels like customer name, issue type, and priority. Just saying please return JSON is unreliable. The model might add extra ticks or missing fields. The structured outputs force the model to return data in exactly the format you specify. So how do we force valid JSON? You define a schema, a blueprint that describes what fields you want, what types, and which are required. Then you pass it to the API using response format. The model literally cannot return anything that doesn't match. No extra text, no missing fields, no wrong types. JSON, by the way, stands for JavaScript Object Notation. It's a standard format using key value pairs. Curly braces for objects, square braces for lists. Almost every programming language can read it. Last but not least, never trust LLMs output blindly. Even with structured outputs, always validate. The JSON might be a valid structurally, but the content might not make sense. A confident source might be negative. The model might hallucinate, meaning it confidently makes up information that's not true. Always add a validation step. Parse the JSON. Check the values. Handle errors gracefully. Golden rule, treat LLM's output like user input. Helpful, but not potentially wrong. Alright, everyone. We have covered a lot in this model. let me tie it all together so you can see how every concept connects into the big picture. What I call the GenAI Stack, when you type a prompt and send it to an LLM. Here's what actually happens under the hood. First, your text gets broken down into tokens. Those small pieces of words we talked about at the very beginning. Then, each token gets converted into an embedding, a list of numbers that capture the meaning of the token. These embeddings go into the model, where the attention mechanism figures out which tokens are related to each other, no matter how far apart they are in your text. All of this happens within the context window, which is the maximum amount of text the model can see at once. The model that generates output tokens one at a time, and the temperature and sampling settings you choose control how creative or predictable the output is. You interact with this whole system through the API using messages with roles like system, user, and assistant. And when you need reliable, machine-readable output, you use structured output to force the model to return clean JSON. Every single piece builds on the others. That is the full GenAI stack. Here's your cheat sheet. Bookmark this, screenshot it, everything. This table summarizes every key concept from the entire model in one place. Tokens are the building blocks. Everything starts and ends with tokens. Embeddings capture meaning as numbers, which is how models understand that king and queen are related even though they're spelled nothing alike. The context window is your hard limit. Go over it and the model starts forgetting things. Temperature is your creativity dial. Top P is a smarter way to narrow down token choices. Messages and roles give you control over the conversation structure. System sets the rules. User asks questions, assistant responds. And JSON nodes ensure you get clean, parsable data out of the models instead of free-form text. If you remember nothing else from this model, remember this table, please. And that is a wrap on GenAI Foundations. You now understand the core building blocks of how large language models work, from tokens and embeddings all the way to structured outputs. This is not just theory, these are exact concepts you need to build to build real AI-powered applications. Now, here's what I want you to do next. Please, go try the hands-on exercise in the platform. They will let you play with actual API calls, experiment with different temperature settings, and try building something that pulls everything together. The best way to learn this stuff is by doing it. If you have any questions, drop it in the comments or join in the community. And if this video helped you, smash the like button and subscribe so you don't miss a thing the next model. Keep building, keep experimenting, and I will see you in the next one. Bye-bye.